This lecture is part of an online course of multivariable calculus, and I'm going to talk about applications of parametric surfaces. So if we have a surface, a general surface in R3, we say that it's parametric surface if we can parameterize it using two parameters, u and v, and we say that it's a vector function with the coordinates x, y, and then z. Each of the coordinates are functions of u and v, so we need two parameters u and v to parameterize our surface, where our parameters u and v are in a region in R2, basically in UV plane. Okay, so one application of these parametric surfaces is to find actually the tangent plane to the surface S. Okay, so if we have, like, assume that we have, for example, this is my surface in R3, and then I'm looking for the tangent plane to this surface at the point P, for example. So I'm looking for this tangent plane. For any plane, we need a normal vector, where the normal vector, we show it by n, and the normal vector is a vector that is perpendicular to your plane. So we need a normal vector, to write the equation of a plane, we show it by n, and we need a point in the plane, a point P0 in the plane. So we are given the point P0, and then I'm looking for the vector n to be able to write equation of this plane. So how can I find this? Well, I'm saying that at the point P0, if I'm given the parametric equation of the surface S, I can divide, I can find actually the partial derivative of r with respect to u at the point P0, okay, which is what? Which is partial derivative of the first coordinate with respect to u, partial derivative of the second coordinate with respect to u, and partial derivative of the third coordinate with respect to u, and compute this at the point P0. In that case, I found this vector in here, which is the vector r of u at the point P0. Okay, let me just make my graph a little bigger so that it is more understandable. Very good. So this vector is tangent, so the vector r of u is tangent to my surface. At the point P0, I have this vector. Then I can differentiate the parametric equation that I have with respect to the second parameter at the point P0. So I'm taking derivative of x with respect to v, taking derivative of the second coordinate with respect to v, and the third coordinate with respect to v at the point P0, and then just assume that this vector r with respect to v at the point P0 is the second vector, this vector, and both of these vectors, because of definition of partial derivatives, both of these vectors are actually tangent to S at the point P0. Let me write this down. RU at P0 and RV at P0 are both tangent to S, and so these two lie on the plane that I'm looking for, on the tangent plane. Okay, so if I take the cross product of these two, the cross product would be perpendicular to S. Okay, so the vector n that I need in here, the normal vector, I can define it as r with respect to u and the parametric equation of S with respect to V, and then the cross product of these two at a point P0. Very good. So I found the normal vector that I was looking for. I'm given the point P0. I can write equation of the tangent plane. Okay, let's look at one example. Example is this. Find the equation of the tangent plane to the surface given by r of u and v equals to u square I plus uv plus v square j plus v e to the u k at the point 0, 1, 1. Okay, so let's look at the solution. First, I need to find the normal vector to the tangent plane. The normal vector would be partial derivative with respect to u, cross product with partial derivative with respect to v. So r of u is equal to what? It's equal to 2u. I'm taking derivative of that with respect to u, derivative of this with respect to u, and derivative of that with respect to u, v e to the u. So at the point 0, 1, 1, what is that? So this is this point is given. I need to find parameters at this point. Okay, so this point says that the first coordinate is 0, the second coordinate is 1, and the third coordinate is 1. So based on that, u is equal to 0. And then look at here, u is equal to 0, so I have e to the u times v is equal to 1, meaning that v is equal to 1. And let's check my answer. uv is equal to 0, and then v squared is equal to 1. Perfect. So at this point, these are my parameters. So I'm gonna plug in u equals to 0 and then v equals to 1, okay, which are the parameters at the point 0, 1, 1. Okay, so r of u at the point P0, it's equal to u is 0, v is 1, and then this is r of u. And then r of v, let's take derivative of that with respect to v. This would be 0. Derivative of that with respect to v would be u plus 2v. And then derivative of this one with respect to v would be e to the u. And so again, at u equals to 0, v equals to 1, r of v at p0 would be 0, u is 0, v equals to 1, 2, u is 0, so e to the 0 is 1. Okay, now n is the cross product of these two, r of u, cross product rv, which is equal to what? I, j, k. Ru is 0, 1, 1. Rv is 0, 2, 1. Okay, so the first coordinate would be 1 minus 2, negative 1. The second coordinate, 0. The third coordinate is also 0. Okay, so that's the normal vector. So the normal vector x minus the first coordinate of the point plus 0, the second coordinate of the point, minus 1 plus 0, the third coordinate of the point. 0 meaning that x equals to 0. That's the tangent plane. Tangent plane. Okay, let me show you to the graph. So you see, this is parametric equation of the given curve. Okay, if I want to change it from, for example, let me change it from negative 10, and then so that I have a better approximation of the shape. You see, that's the shape of this graph. It's kind of, you see, this is x-axis, this is y-axis, and then if I zoom in, you see, this is the graph of this shape. That's very nice actually. And then let me see, at the, let me bring up x, y, and z plane. Lost. Okay, so this is x-axis, and then at the point 0, 1, 1, so x would be 0, y and z would be 1. So I have this as the tangent plane. At this point, you see, it's a tangent to this curve. Okay.